Okay, let's get started. So hopefully you're in the right class. So this is EEL6532. So it's in information theory. Okay, so yeah. Oh, why? Yeah, why there are two pages? Let's see, view slideshow. Okay, good. Yeah, so first of all, let me introduce myself. So my name is Mingrui Ji. I'm an associate professor here. So my office is here is 42. Oh, I think there's a mistake here. Is it? 4214. So is that my office? Yeah, probably is. Yeah, I never see my number there. Just write something there. Probably that is right. So this is my email. So. And you can contact me anytime. And this is my website. So I have a YouTube channel. Probably, yeah, I think this should be the right YouTube channel. But yeah, I'll double check with it. So basically, I'll put all my lecture notes on the YouTube, and you can watch it at home. Okay, so maybe we can check it a little bit. So basically, yeah, this is the channel from what my view, your channel. Yeah, so this is basically my channel here. Okay, and today I just uploaded a lecture of information theory, so which is our class, but this is an old lecture. Okay, so this is not a new lecture, so I'm going to record all my new lectures, okay? So the content will be updated a little bit because, so this lecture was recorded in 2021 probably. So yeah, because of COVID, then we do everything online, so I record my lecture there. So most of the content will not be changed too much, but it'll be updated because now there's some crazy development for AI. So as you may know, so information theory is applied a lot in artificial intelligence, especially machine learning, like this foundation model learning training, right? So I may update a little bit, so put more focus on, more modern topic, but probably like 80 to 90% of the content will still be the same. Okay, so yeah, because our lecture, the time is very limited. Every time is 15 minutes, right? So but when I recorded, I didn't care too much about the time, so I may put more detail there. Okay, so if I have to skip something in our lecture, I'll tell you where you can find it for my old lecture. Okay, you can take a look. Okay, so this is my YouTube channel, so you can see it. All right, so yeah, let's get back. So to the slide. Okay, and so a bit introduction of my research lab. So my lab is called Edge AI, or Edge in Artificial Intelligence. So those are the 4 topics that we do a lot, right? So first of all, we do both theory and practice, right? So basically means that we do theoretical proofs and we do algorithm designs, and we also do practical implementations, right? So we have a lab in the 6th floor, and we did implemented lots of IoT, Internet of Things, network systems, and also we implemented lots of edge computing and wireless networking prototype there. Okay, so if you're interested in doing any kind of research related topics, feel free to contact me. Okay, so we have lots of projects available to talk about, right? So just a very brief introduction for information theory. So basically, I don't know. So who will know a little bit about information theory? Only one? Okay. Oh, great, too. Okay, great. So I don't know. What do you think about information theory? So is that relevant or not so relevant nowadays?
Probably relevant.
Probably relevant. Yeah, but why we have so small classes, right? If it's very relevant.
Probably because it's not super easy, I would assume.
Yeah, that's correct. That's correct. So how about you?
I think it's relevant.
Mm-hmm. Okay, so yeah, very good. What I would say is that information theory was extremely relevant before 70s. Okay, so none of you were born by that time, right? So probably you were born like after 2000, I guess. Okay, so before 70s, the information theory is very relevant after Shannon, right, for the seminal paper from 1948. Okay, and right after 70s, there's a big stop for information theory. The main reason is that so people do not have very good idea on how to progress it. One big reason, there are mainly two big reasons. The first reason is that it's too hard and the people do not have any very good idea, but probably that's not the most important reason. So do you mind to close the door if possible? Yeah, thanks. So the other reason is that there's no big application of it, right? So as you may know, so the first or the biggest successful application of information theory are number one, wireline and wireless communications. Okay, number two, storage. Okay, so at that time, those two are not extremely developed. We have very simple communication system, right? We do not use much, of information theory to develop it, right? But later on, around 90s, so there's a surge of wireless communication and also storage system, right? And then more and more people are involved, realize that, okay, information theory is relevant because it gives you like two very important quantities that we're going to talk about that today, okay? And like huge amount of people coming into this field at that time, right? And then there's a huge development from like 1990s till 2010, okay? So were you born at that time? 2010, okay. So yeah, that's a golden age of information theory. There's so many great results were developed during that time, maybe like 25, 30 years, okay. And then around like 2010, so we have very kind of mature wireless communication system, and the storage is pretty mature as well. And then we need to stick for other applications for information theory, and then we got stopped a little bit, right? So, then like from maybe like 2015 until now, there's no big development for information theory. But a few years ago, due to the fact of artificial intelligence, right? For example, ChatGPT or cloud or whatever, they get really successful now, right? If you know. So do you know what is the objective function for this foundation model, right? To train a model, you need a loss function, right? So what is the loss function for the foundation model? LLM. Know that? Exactly, it's a cross entropy, right? So that's a concept from information theory that we're going to talk about that very shortly, okay? So we believe that information theory will be more relevant, right? So as you show in this slide, right? So we can say that information theory is a fundamental of many things, right? Including, as we said, communications, networking, computing, storage, right? And also artificial intelligence, okay? And so you may not be able to see this very well, but you can see that. So information theory is not, it's an idea, but it's not, so it's fundamental theory, but it's still an application of math and other subjects, okay? So basically, it's a very difficult course to teach, right? So the math is pretty hard, but it's not terrible. Okay, so normally people can follow the math pretty well, okay, but the more importantly, we need to understand the idea of Shannon. Okay, so Shannon, by the way, is the inventor of information theory, the father of information theory. Some people say that he's the father of artificial intelligence, the father of many stuff, okay, but I think the most brilliant contribution of Shannon is to give you an idea on how to think about that. Right, that is the most important thing. Okay, I will not say the math is the most important thing in our class, rather than the idea how to think about things. Right. So how to prove a thing, how to prove something that exists without constructing it. Okay. So we know. Okay. So we know there exists some scheme can achieve this kind of bound, but how to constructing that is a different story. Right. How can we came up this kind of nice idea? Okay, I think that is very important, right? We should have this kind of training in our mind, after this class. Okay, so yeah, that's a very brief introduction here. Okay, so next, so this is the outline for our class. So we're going to talk about syllabus, introduction, and what is information. Probably don't have time to talk about the last bullet, so we're going to continue next class, okay? And now let's talk a little bit on the syllabus, okay? So I'll make it bigger. So so this is our syllabus, okay? So uploaded on Canvas. Hopefully all of you can see that, okay? So we have a course website here. So basically, for all my classes, so I use two things. One is Canvas, and the other one is a website. Okay. So if you like Canvas, just use Canvas. Otherwise, you can use the course website. They're identical. Okay, exactly the same. Okay, no difference. So no. So where's the course? Yeah, here's the course website. Yeah. So now this is what it looks like. Okay, and later on, so I'll go into. I didn't do that yet, probably. No, I didn't. So I'll upload. If you click syllabus, you will see that, and if you click lecture notes, you'll see that. Okay, and for each lecture, for some of you who have taken my class before, you'll know that. So basically, for each lecture, I will go over what we learned in the last lecture by using some lecture review slides. Okay, so to remind you a little bit what we covered in the previous lecture, and then so I'm going to write down everything using my tablet. Okay, so, because this class is mainly theory, so there might be there will be some small exercise for programming and so on, right? To practice coding a little bit, but 95% will be theory. Okay. But I will talk about applications, but in terms of homework and so on, it will be just mathematical computation. Okay. Okay. Let's and this is our lecture time and location. Okay, for office hours, so normally I don't hold fixed office hours, right? But I'm very flexible. I have an open door policy, so if you want to ask a question, just come direct to my office if I'm there, so I can answer a question directly. Okay, and the other thing is that you can send me an email, so we can do this by appointment. So I'm available every night via Zoom, right? So we can schedule Zoom call if you have questions. Okay. Great, still recording. All right. So okay, this is a course description, and you can take a look at this. So basically, so everything is from this seminal paper, A Mathematical Theory of Communication. Okay, and so I didn't put this paper. It's a small book, actually. It's about 55 pages. So I think in 1948, it was published in Bell Labs Journal. It's a journal paper. In the next year, it will be, I think it was published as a small book. Okay, it's a very, it's a very simple, not simple, it's a very easy to read paper. So I have this paper here, you can take a look. So basically that is this paper. So I'll suggest everybody read this paper, okay? So normally when people teach information theory, they normally do not start from this paper, right? So because, this theory has been developed since 1948, there are many approaches to teach this class, okay? So, but what I'm going to use is that, so I learned this from an extremely famous guy called Jin Zhang, and and his advisor is Toby Berger, so which is an extremely huge guy in this field. So I learned information theory from them. Okay, also from my advisor Giuseppe Cari, who is a professor in Germany now. So my approach will strictly start from this paper. Okay, you'll see how Shannon came up with this brilliant idea, right? Instead, just telling you, okay, so this is definition of entropy, this is definition of mutual information, and and then we're gonna see what property that is. I'm not going to do in that way. Okay, so many people do it in that way, but what I'm going to do is that I will start from this paper, and introduce you the idea. Okay, so by the way, so did you have any idea of how large language model work? No? A little bit. I will show you a very good example. So I'm pretty sure that not many people realize it. So In this paper, there's a very nice example showing you that, okay, so if we want to generate some, let's say here, generate some text, okay, how can we generate it, right? So we know, hopefully all of you learned a little bit for probability theory, okay? So let's say if we generate the text using a zero-order approximation, what zero order basically means that every letter will be generated uniformly. We know that we have like 26 letters and we have one space. Okay, so in total we have 27 choices. Okay, so if we generate all of them uniformly at random, okay, therefore, so each one will appear with a probability of 1/27, right? And this is what you get. Okay, it's not a language, right? But then if we do something better, right? So if we do first order approximation, basically means that each letter will still be generated independently, okay? But with the right distribution, right? So we know, we have all the books, right? So we can, do the statistics of the distribution of each letter, right? Then we know probably E will appear much higher probability than letter Q, right? And if we use the right probability to generate all the text here, so this is what you get, okay? Still not language, right? By the way, I'm doing English, right? So not other languages. It's not language, okay? But still not good enough, right? But let's do the second order approximation. Basically, if we use a Markov structure, right? For example, let's say if I have an A, right? Then what's the next letter? Probably B with higher probability, and maybe some Z with a lower probability, right? So let's say if we just look at the first letter, the letter before me, and then use a Markov model to generate the next letter. So this is what you got. Okay, still not good enough, right? And then if we let's keep things more involved, right? So you can read it, but lastly, what we do is that if we use this Markov model on words instead of letters, Markov model on words, right? And then this is what you get. The head and in frontal attack on an English writer that clear, that the character, right? So if you see, it's almost language, right? So this is what Shannon tell us, right? We just use a Markov model, first order Markov model, very simple model, and then we can generate something much look like a language, right? This is almost the idea of the large language model. So what it does is that, okay, so give me all the input. I'll predict the next letter, next word. How can I predict next word? Okay, it's using the probability, right? If we maximize the probability distribution, and then we're going to get the next word, right? You can see that's clearly from Shannon. Does that make sense? Okay, so we're going to talk about that in much detail in class, right? This just give you a sense, right? Lots of ideas, answers are from this paper, okay? I don't think people remember it, right? So I strongly suggest you to read this paper. It's very, very well written paper and very easy to read. Okay, great. And now let's go back to our syllabus. Does that make sense? Yeah. Okay. Syllabus. Okay, great. And the learning objective, you can read it. So basically, I told you already, right? We need to, grasp the idea of information theory, right? Really understand what the basic idea. For the prerequisite, I don't have any, right? So whatever the prerequisite required before. So the only thing I need is that, of course, calculus, right? We have to know that, right? And the other thing is that basic probabilities, right? What are the probability distribution and so on. And then we need to understand the random process a little bit. We're not going to use very complicated idea from random process, but we do need the most basic concept of it, right? But I will introduce that in class. So if you have no idea what that is, don't worry too much about it, okay? And then next is a grade distribution. So in this class, it's it's a graduate level class. We don't have any labs, right? And so homework will be like 20%. So we'll have maybe like a number of homework. I couldn't recall what kind of homework, how many times, but we have maybe like 4 or 5 times homework. Okay, and all the homework will be using our textbook. Okay, and I'm going to tell you what the textbook is, but not all, I think most of the homework problems were from our textbook. Okay, they are challenging, they are very challenging. Okay, textbook is a very, very easy to read, simple textbook, but the homework, some of the homework are like research problems. Of course, all the research problems, right? All the problems are solved already, but yeah, they're pretty nice. Okay, so what I'm going to do is that I will probably upload the homework video. So I have a video. I either go over that in class or I'll upload the homework video, right? You can watch it, right, if you want. But I suggest you to, do it yourself. If you don't know how to do it, just watch it. Okay, so of course before the deadline, right? It's not like because this is a graduate level class, right? Most of you are graduate students, right? So you know how important learning is, right? I don't want to, you are not, undergrad or elementary student anymore. So yeah, basically I'll give you the answer before the homework is due. Okay, but they're challenging. And then midterm and final. Okay, so midterm will be 30%, final will be 50%. Okay, so basically most of the grading will depend on the exam in this class. Okay, so the midterm will cover the first half of the class, and the final will be comprehensive. Okay, so the reason we make final to be comprehensive is that in my opinion, first half is more important than the second half. Okay, first half tell you mainly all the important ideas. The second half are kind of application of those ideas. Okay, so you need to really remember the first half. Okay, and so I haven't decided yet, but there's a chance that exam will be take home. Okay, depends on normally for a grade level class I do a take home exam. Okay, but now since you have ChatGPT, so it's really good at doing homework. So I'm still thinking about that, right? So I have we're gonna decide that later. But the exam will not be very hard. Okay, it'll be very basic. Okay, so it'll be much easier than your homework, I would say. Okay, okay, and TA, there's no TA. Okay, only myself, and this is a required textbook, Elements of Information Theory. Okay. And let's see, do I have this book here? No. Oh, I did. This is a book. Yeah, so this is how the book looks like. Okay. I think you can download this from somewhere, or I strongly suggest you to buy that. So it's a very, very good book. Okay. And written by Tom Cover. So he's, again, another Tom Cover and Joy Thomas. I think both of them passed away already, but yeah, they're a guru in information theory. Okay, strongly suggest you to buy this book. Super nice book. Okay, so that's basically our only textbook required. Okay, and so if you're interested, so there's another book, Network Information Theory. Okay, so this is, I would say that, so this book is like a dictionary, right? So meaning that if you want to find some result, then go to this book to find the result, and then check the proof. So there is very little intuition in that book. Okay, so personally, I don't like that book a lot because you need to have lots of background in information theory to understand what this book is talking about, because it really lacks intuition in that book. Okay, and here are the grades. And you can take a look. So basically above 90 will be A, and from 85 to 90 will be A minus, and so on, right? And so normally I don't curve unless all of you did a pretty bad job, so I may curve, right? But based on my past experience, I think so A should be pretty straightforward. It's not very hard. Okay, homework would be hard, but I give you the answer in front, right? And exam would be just basic stuff. Okay, it's not challenging. Unless all of you did a very good job in the midterm, then final will be harder. So, okay, and then attendance policy. Attendance is not required. It's definitely encouraged, right? So I don't want to teach in front of empty classroom for sure, right? But in case if you are not here, then as I said, right? So learning is the most important thing, and I have videos, so you can watch it at home. Okay. Okay, and there's no makeup exam. Okay, so if you cannot, normally if it's a take-home exam, then you have like at least 48 hours to finish it. Okay, so if it's take-home, then the exam will be designed for like 2 hours, and you have 48 hours to finish it, right? But if it's in class, then it will be like 50 minutes. There'll be fewer problems. Okay. Yeah, final will be like 2 hours, no matter what. Okay. Yeah, this is a homework. Every like 2 weeks, you may have a new homework. Okay, and so the scale of the homework will be like from 0 to 10. Okay, and so normally, the grading will not be based on whether you can do it correct or not, right? Because I give you the answer already, right? So if you give me all the questions, and then I'll give you 10 points. Basically, that's how it works. Okay, and also so late policy. Okay, the late policy is as follows. So if you if you're late for X days, and then you'll be subtracted by 2 times X. Right? I have an example here. Right? If you're late for 1 day, and then you got 9, then you got 7. Okay, and weekend doesn't count. Okay, for example, if the due date is Friday, and then you give me on Monday, then I will only subtract 2 points. Okay, so this is the late policy. Okay, all the homework will be due 11:59 p.m. on the due date. Okay, right. Exam, teaching method. Yeah, so you can read those. Those are not super important. Okay, so those are the tentative content for our class. Okay, so we're gonna probably cover those kind of topic, and we may not have time to cover topic 7. Okay, so this is a tentative, but if you don't have time to talk about topic 7, then I think you'll be okay, because you should be able to easily understand those based on what we have learned. Okay, and in addition, so if we may cover some other more interesting topics. Okay, that a modern use of information theory. Okay. Collaboration. Okay, yeah, you can collaborate for doing homework, right? So if you think, my solution is not clear enough, you can talk with your classmates. Okay, you can solve it jointly. So if you solve the homework with others, just put the other's name in your homework, right? So no point will be deducted. Okay, so all points will be given, but just to be clear, so no cheating is allowed. Okay. So by cheating, it's very hard for me to tell, right? So yeah, I will suggest you that don't copy my solution. Okay, that's not good for you. Right? Do the homework on your own. Okay, I guarantee that you will learn a lot. Okay, but no cheating and plagiarism. Okay, and then you can read all the other university policy and so on here till the end. Okay, yeah, I think that will be the syllabus. So if you have any question, just let me know. Okay. Great. Okay, so now let's go back to our slides. All right, let's see. 25. So we have until 50, right? So yeah, we start at 50, right? So we finish at 40, right? 1:40. Okay, we have 15 minutes to go. Okay, great. And so let's talk a little bit about introduction. Okay, so as we said, right, information theory starting from the seminal paper. Okay, and so basically this paper can answer the following 3 questions. Number 1, what is information? Okay, what do you think? So what is information? Yeah, based on your understanding, of course. Don't need to be precise. Bits. Okay, bits. Yeah, that's kind of the second question. How do we measure information, right? But what is information?
Data that can be useful.
Data that can be useful. Very good. It's very close. Yeah, I think that's a very nice answer. Anything else? Yeah, data, right? So what is data? Why do you want to know the data? Because you don't know the data, right? So what is something you don't know? Yeah, that's basically information.
That's already something that you know. Could it be considered something?
Huh?
If I know that I don't know something, do I know that thing? Like, or something about that thing?
Yeah, well, it's a kind of a philosophical question, right? So, yeah, I think you partially know something, but you partially don't know something in that case, I guess, right? So basically, from Shannon, so he tells us that information is uncertainty, right? So if we want to know some data, it means that we're not certain about it, right? For example, if we toss a coin, right? So can we gain any information from the result? Head or tail? Yes, right? Because we don't know the result before we toss a coin, okay? Basically, it means that we have two options or two possibilities, heads or tail, right? And then if we toss that and if we see it's a head, then we know, okay, it's a head, right? Then we remove uncertainty. So we don't have this uncertainty anymore. Does that make sense? Right, that's the information, uncertainty, okay? So that's, it's kind of axiom, right? So we need to agree on that, right? If we don't agree on that, then we cannot continue. Yes?
Is information when uncertainty gets answered becomes certain? Because uncertainty is just uncertainty.
Yes.
Right?
Yes.
Okay, so it's when uncertainty becomes certain?
Yes.
Okay.
Then you gain information.
Yeah.
Yeah.
Okay, makes sense.
Yeah. So if they're still uncertain, there are information, but you just don't know that yet, right? Once you know it, then you know the information. Okay, that's how it works. That's how it defined. Okay, great. And the second question is, how can we measure information? Okay, and this is kind of hard to say, right? So, but we can still use the example of flipping a coin, right? So if I flip a coin and then you know whether it's a head or tail from don't know it, what do you think? How much information you get? Right? Before we have two possibilities. So can we use a digit number to quantify it? 1 or 0, right? 1 is a head, 0 is a tail. Okay? And if we do not flip it, and we have no idea about it, but we know either it's a 1 or 0. Okay? But if we see it, we know for sure it's a 1 or 0. Okay? And for this binary variable, we can use the concept called how I just said, right? It's a bit. Does that make sense? So if we see it's head or tail, we say we gain 1 bit of information. Does that make sense? Yeah, it's intuitive, right? Later on, we're gonna see that it may not be the case. Okay, but the idea is from there. Okay, so think, okay, so that's actually, the information theory before Shannon. Okay. Oh, by the way, so before Shannon, before 1948, we do have communication and a storage system already, right? We even have digital communication, right? For the telegram, right? So we have telegram, we have telephone, right? We can make phone call. Probably phone call is analog communication. Oh, by the way, I forgot to mention that when we talk about the information theory, so everything is digital. Right? We still talk about analog, but we need to transfer the analog signal to a digital signal first. Right? So who knows what is the analog signal, what is digital signal? Yeah, no problem. So yeah, so everything I said today will be covered in much detail later, right? If you don't know that today, it's not prerequisite. I don't worry too much about it. So digital basically means that we can use discrete number to represent something. Okay. Everything has to be digital, okay? And as we said, right, so if we flip a coin, and then probably get 1 bit of information, right? So, but that's before Shannon. So what Shannon tell us that if you flip a coin, the maximum amount of information you'll get is 1 bit. It is possible to get less information than that. Why it is possible? It's because, so the coin may not be a fair coin. Let's say 90% of the probability is head, 10% probability is a tail. Then before you flip it, you have some idea already, right? 90% will be a head and 10% will be a tail. Your guess is probably a head, right? then once you see the result, it's ahead. Then you don't gain as much information as that for a fair coin. Does that make sense? Right? It's pretty intuitive, right? Yeah. So that's what Shannon tells us. Okay. Yeah, it feels too simple, right? So there will be more complicated stuff. Okay, so now we know what is information and how do we measure information, right? The next thing is that how can we represent information? Okay, so we have two topics here, okay, from Shannon, okay, but later, we have a lot more than that, right? So Shannon tells us that, okay, so we need to consider two things. So in order to represent information, we need to understand how to transmit information in space, right? How to communicate information from me to you. Okay, that's number one. So it's called, information in space. So this introduced the communication system. And the other one is how to, represent information in time, meaning how to record the information. So that means the storage. Okay, that's the storage system. Okay, so those two, communication and the storage. So those two are the most basic application of information. Okay, so we're going to focus a lot on these two kind of systems in our class. Okay, so many ideas are from that. So we're going to talk about that now. So consider a communication system, right? So communication system and the storage system, they are not separated, right? Because we do need to, have our information stored somewhere and then transmit. Okay, so when we consider, let's go over this figure first, right? So this is a typical communication system. So if you take communication theory class, probably you have seen that already, right? So it starts from the information source, right? The information source can be anything, right? For example, it could be a file, could be an MP3 music, could be a video, could be, if we make a phone call, could be, my voice. So all of those are source information, okay? And then we need to transmit it, okay? How to transmit it? So yeah, we cannot just transmit the source file directly, right? The reason is that we have a media in between from the transmitter to receiver. The medium can be a wire, right? Can be optical fiber, okay? Can be coaxial wire, right? Or can be wireless, right? Like say, so if I make a phone call to you, so my phone will be connected to the base station, and then the base station will connect to you, and then this is how we make a phone call, right? So I have a medium. So this medium depends on the frequency property, right? So the signal, only the signal with specific frequency can pass through this kind of media, okay? It means that we need to modulate the signal to something and then transmit, right? It means that we need to do some signal processing before transmit to make the signal fit for the transmission media or the channel, okay? So this is what the transmitter is doing, okay? And then after the channel, so normally the simplest channel we have is so-called the additive noise channel. So we add some noise to the channel at least, right? There'll be some other factor in, we're not focused too much about that now, but the channel will distort your signal, okay? And then you need a receiver. So this is a signal processing block, that recover your signal, okay, and make it ready to the destination. Where the destination is basically the source decoder. It can decode information, right, from digital whatever 1 zeros to whatever you want. For example, like a music or voice or video and so on. Okay, so this is a communication system. Okay, and for this part, information source and destination. So we call that. So this is the storage problem. Okay, and we call that the source coding problem. So which means that we want to make our source as small as possible. Okay, because storage is still precious, right? And or even in terms of communication, so we want to remove redundancy, okay, and make the source as small as possible. Okay, so this is the first Shannon coding theorem called source coding theorem. It tells you that, okay, give me some source, okay? Give me the statistics of the source. Let's say, a source, basically a number of symbols. It could be 0 and 1. It could be 1, 0, 1, 2, or whatever, right? So for each symbol, there will be some probability distribution. As long as you tell me the probability distribution, and then Shannon can tell you what is the smallest amount of bits you need to store that. So that's the source coding problem, And this is very, very related to what? Cross entropy, the loss function of what LLM used today. Okay, so if you think it, actually nobody can understand large language model in a strict mathematical way, but we have lots of intuitions. Okay, one intuition is that, okay, so the large language model should compress your information, right? So in machine learning, we need to represent information, right? But the right way to do it is that we want to represent each information in the most efficient way, right? So this is related to this problem. Okay, very good. And then the next one is a second coding theorem. It's called, so this is, okay, so now we know the transmitter, and we know it's a receiver, and then how to communicate information, right? For the source coding problem, we want to make, the amount of information as small as possible, right? Or number of bits as small as possible, right? But for this channel coding problem, we want to make sure that whatever is transmitted here, and that is what is received here, right? We transmit a 1, and then we want to receive a 1. So we don't want to, okay, if we transmit a 1, we don't want to receive a 0. That's a mistake, right? It's not good. But how can we deal with that problem? Any idea? Yeah, you should know that, but don't say it. Any idea? Let's say I just transmit the 1. Let's say I can transmit the 1, right? Transmit 1 to you. There maybe, let's say there are half chance, that will be in the error. What is the most intuitive or the simplest way to make it better? Exactly. How do you know that? So yeah, it's transmit twice, right? Yeah, just compute the probability, right? So if transmit 1, the error probability is 0.5, but if you transmit twice, twice is not a good idea. Let's say 3 times, that's better, right? If we receive 2 1, we say, okay, it's a 1, right? If you compute the probability, then we get much better. So now it means that if instead of transmitting the signal 1, we transmit it 3 times. We transmit more, okay? We add redundancy, right? So therefore, you can think, the channel coding is doing something kind of in the opposite of source coding. Source coding is to remove redundancy. The channel coding is to bring more redundancy to overcome the error that happened in the channel. Does that make sense? Okay, so this is the two most important theorem in this class, the source coding theorem and channel coding theorem. Okay, and by the way, so cross entropy is related to both of them. Okay, so we're going to learn a lot about that. And in addition, okay, so as we said, right, so those are introduced by Shannon. Okay, but after Shannon, there are so many great information theorists, right? There are many other applications for information theory. So nowadays, modern information theory is much more than that, much more than source coding and channel coding, okay? And as you see here in my syllabus, so we say that if we have time, so we may want to go over some other topics, for example, like a distributed storage system, right? Small storage, but it's distributed, like private information retrieval, okay? Like a distributed computing, like cloud computing, Amazon EW2, right? It's all, so many things, most of them can be explained using information theoretical tool, okay? So still, it's a hot field that is developing, okay? So I think that's probably what we are for today. And from next lecture, so I'm going to use my tablet to write down all the math. Okay, so from next lecture, it'll be pure math. Okay, yeah, thank you.